Yeah, hopefully for the last time I'm asking, you are able to see the screen, right? Okay, good. Fine. So what we will do is I'll start with the oscillators. All right. So this is module. I'm so sorry. It's module 4B. Oscillators. Now, have you studied about oscillators in basic electronics? Something about oscillators you have studied in basic electronics. Okay. All right. So oscillator, okay, basically it's a circuit which produces periodic output waveform. Okay. So oscillators, it's a circuit which produces a periodic output wave. Since it is producing, you know, an output waveform, you can also call it as wave generator. It's a waveform generator. Waveform generator. All right. Now, you have studied about amplifier. Amplifier also produces a waveform. So oscillator is also producing a waveform. So what is the difference between amplifier and oscillator? Both are producing waveforms, right? So then there has to be some difference between the two, or else why would they call this particular circuit as oscillator? Okay, the major difference between oscillator and an amplifier is that your amplifier circuit takes input as some physical AC input and gives the output as some AC output. That means to say your amplifier takes small small signal AC input and gives normally large signal AC output. Okay, so this is your normal amplifier operation. Okay, now if you look at oscillator operation, okay, the oscillator also can be represented with a black box. Okay, let us not worry about what components it is uh, made up of. Okay, we'll talk about it later. Okay, the major difference between oscillator and an amplifier is that your oscillator doesn't require any physical input. Okay, in a sense, let me correct my statement. Oscillator doesn't require any physical AC input. So let me write no AC input. Okay. Even then, the oscillator gives AC output. Okay. AC input is not there. There is no AC input, zero input. But it gives an output. Okay, that means to say it is something like regeneration circuit. Out from nothing, your circuit is capable of generating a waveform. Okay, that is called as oscillator. Okay, and it is possible only because of one factor, that is, it simply takes the power input from the operating DC voltage. Okay, so this operating DC voltage is used in amplifier also, because this VCC is being used to establish Q conditions or the biasing conditions. The same VCC is also used in oscillator to establish Q conditions. Okay, but in case of oscillator, the circuit exploits this power supply, DC power supply itself as the kind of pessimistic input, and it gives periodic output waveform. Okay, so that is the major difference between oscillator and amplifier. That's the reason sometimes oscillators can be roughly can be called as inverters. not the proper definition, but roughly you can call them as inverters. That's because it takes only DC as the input and gives AC as the output. Correct. So DC to AC conversion is called as inversion or inverter operation. Okay. So you can also call them as inverters, or you can also call them as waveform generator, because out from nothing it gives a periodic waveform. Now for the representation sake, I have drawn a sinusoidal output. Okay. Now it need not be a sinusoidal output. That's the reason I have used the generic term called periodic waveform. Okay. Now what do you mean by periodic waveform? A periodic waveform is nothing but a waveform. It repeats itself one cycle after the other. In a sense, what is present in 0 to 360 degree duration will present for 360 degree to 720 degree duration as well. Okay, so in every cycle after the other, the wave shape repeats itself. Okay, that is called as periodic behavior. Okay, now classification of oscillators. Okay, oscillators are broadly classified into two types. Okay, sinusoidal oscillators and non-sinusoidal oscillators. Okay, as you know, the sinusoidal oscillators are those oscillators which gives the output in the form of a sinusoidal signal. Okay, now in our syllabus, we will be talking about um, sinusoidal oscillators. We will not be talking about non-sinusoidal oscillators, because non-sinusoidal oscillators are dealt in detail in a course called linear integrated circuits that you are going to study in fourth semester. All right. So in this particular semester, that is in the third semester, let us only study about sinusoidal oscillators. Okay, but let me give you an example for non-sinusoidal oscillators as well. Okay, the waveform which is not sinusoidal is called as non-sinusoidal oscillators, right? For example, square waveform. Okay, Schmidt trigger can be used to generate, a square waveform, or you can also have, this triangular based oscillators. Okay, these are all examples for non-sinusoidal types of oscillator circuits. More of it you will be studying in a subject called LIC. All right. Now, that being told, that is about the classification of oscillators and the definition of oscillators. Probably now I can talk more about the feedback mechanism in oscillators. Okay. Now, the type of feedback used in oscillator is different from the conventional closed loop circuits. Okay, so the type of feedback used in oscillator is positive feedback. Okay, I think I have told you about it, right? When I was dealing with the feedback amplifiers chapter. Hmm? Now, what is this positive feedback and what is this negative feedback? I've already spoken about positive and negative feedbacks, right, in the feedback amplifier chapter. Correct. Now, uh, negative feedback is a feedback in which the feedback signal and the input signal are in out of phase. Okay. So in case of negative feedback, feedback signal and the input signal are in out of phase. Okay. On the other hand, in case of positive feedback, the vice versa condition holds good. So in case of positive feedback, feedback signal and input signal are in phase. All right. So now what we will do is, let me talk about the positive feedback concept. So let me write this subheading as positive feedback concept. Sometimes it is also called as oscillator concept, or the concept on which an oscillator circuit operates. Okay, generally it asks for 6 marks. Okay, important. All right. Now, to understand the concept of positive feedback, what I will do is I will construct a simple block diagram, okay, of a general system. A system is consisting of forward path elements, okay, with a output sensing mechanism, which is called as feedback. Okay, so let us call this as the amplifier having gain A, okay, amp. And let us call the bottom block as feedback circuit having gain beta. Okay, so beta is the gain of the feedback circuit and A is the gain of amplifier circuit. All right. So let us assume that the amplifier is a voltage amplifier in nature. So output of voltage amplifier is V naught. Okay, and the feedback signal, okay, which is derived, okay, let's call that feedback signal as Vf. Okay, and the external input we shall take it as, let's say, Vs. Okay, so in case of oscillator, as I said, we use positive feedback. That means to say feedback signal and input signal are in phase. In phase in the sense they get added. Okay, so the two signals get added. Hence, the effective input Vi that is getting applied to the amplifier will be the summation of the source signal Vs and the feedback signal Vf. All right. So, with which what will happen is there will be 0-degree phase shift. Okay. Why 0-degree phase shift? I will tell you why 0-degree phase shift. So let's say this is your source signal. Okay. And let's say this is your output signal. Okay, so input is positive going, output is also positive going. So that means to say between Vs and V naught. Okay, so phi, that is angle between V naught and Vs, is equal to 0-degree, right? Similarly, when you feed a part of the output signal to this feedback network, the feedback network produces a feedback signal. Let's say this feedback signal is represented by Vf. Vf. Now, this Vf, if you look at, okay, this Vf is also having the same phase as that of Vs and V naught. Hence, the phase of, that is phi of Vf and Vs is also 0-degree. That means to say, in case of positive feedback concept, or in totality you can say that in case of oscillator circuit, the total phase shift around the loop should be 0 degree or 360 degree, because 0 and 360 degree mathematically considered as the same point. Okay, of course 360 degree will be the starting point for the second waveform, right, and 0 degree is the starting point of first waveform. So in that sense you can say the total phase shift should be either 0 degree or 360 degree. So this is the one very important feature of positive feedback. Okay, in case of negative feedback, there will be a phase shift between the input signal and the output signal. All right, fine. So let us define the various voltages. So Vs is equal to source signal, and V naught is equal to output signal. Okay, and Vf is equal to feedback signal. Okay, fine. Next, let us write down some expressions. Okay, let us define, let AF is equal to overall gain of the positive feedback system. And let us define overall gain AF as the output voltage to the source voltage. Okay. Similarly, let us also define A as the amplifier gain. And let us define amplifier gain A as output voltage to the effective input voltage Vi. Okay, fine. This is say equation 1 and this is say equation 2. Okay, and let us also write down an expression for Vi. What is it, Vi? So Vi is basically the signal that is getting applied to the amplifier block, and which is basically resulted from the addition of source signal Vs and the feedback signal Vf. So mathematically, you can write Vi as the addition of source signal and the feedback signal. Okay, where the feedback signal Vf is nothing but, okay, so Vf is the output. So what is Vf? Vf is equal to input signal, that is V naught, into the feedback factor V naught, beta. So Vf is basically beta times V naught. Okay, where beta is the feedback factor and V naught is the output signal. Okay, so let's substitute 4 in 3. So what do we get? We get Vi is equal to Vs plus beta into V naught. Okay. Okay, that implies source signal Vs, because we need to establish a relationship between output voltage and the source voltage. So let me keep source voltage on the left hand side. So source voltage Vs is equal to Vi minus beta V naught. Say equation 5. Okay. Therefore, I mean, you can substitute this equation. Equation 5 in, let's say, the main equation, right? AF. So you would get AF is equal to V naught divided by Vs. Vs is Vi minus beta into V naught. Okay. And we'll just do some small manipulation. What we will do is, let's divide the numerator and denominator with Vi. So V naught by Vi is equal to Vi minus beta V naught divided by Vi. No harm done, right? Mathematically, the equation still remains the same. Okay, but by doing that, what I will get? V naught by Vi ratio is defined as A, the amplifier gain, right? See, V naught by Vi is nothing but A. So AF is equal to A divided by Vi by Vi is 1 minus beta into this ratio V naught by Vi. That is also again A. So basically, I get the closed loop gain AF is equal to open loop gain A divided by 1 minus A beta. So this is the expression for the closed loop gain. Okay. Now, if you remember, while discussing the feedback amplifiers, we had derived a similar kind of expression, right? And that expression had positive term in the denominator. Okay, so the positive term in the denominator comes into picture for a negative feedback concept. Since we are discussing about oscillator, so we are getting a negative sign in the denominator. All right. Now, generally, in case of oscillator, A is fixed. That is, amplifier gain is fixed at a particular value. Okay, and beta is varied. Okay, so I mean, this is how we try to generate the waveform even in laboratory. Okay, eventually you will get to see how exactly we generate oscillator, waveform, even when there is no physical AC input is present. Okay, what we do is we try to um, play around with the feedback factor parameter. Okay, that means to say we are trying to vary the factor beta, and as you start varying the factor beta, what will happen is you will get some 2 3 crazy kinds of waveforms. Okay, and at one particular value of beta, what happens is that just like that you will get a pure sinusoidal waveform, and that point is called as the condition for oscillation. Okay, I'll discuss in detail about it. Okay, but at this point of time, what you have to understand is that in a practical oscillator circuit, amplifier gain A is fixed and only the factor of beta is varied. Okay. Now, effect. So as beta is varied, okay, what happens is that at a particular value of beta is equal to, let's say, 1 by A. Okay, so when the value of beta becomes 1 by A, okay, because A is a finite number, right? What is A? A is gain 50, 70, 100, whatever it may be. So at a particular value of beta, that is at beta is equal to 1 by A, what happens is that your overall gain AF becomes A divided by 1 minus A into beta. What is beta? Beta is 1 by A. So A gets cancelled. So basically you are left with A divided by 1 minus 1. That is A by 0 or infinity. So what is this AF is equal to infinity? AF is equal to infinity is basically the condition for oscillations, in the sense if you cross multiply this particular condition, what do you get? You get A beta is equal to 1. Right? You get A beta is equal to 1. That means to say, when beta is equal to 1 by A, or when the product A beta is equal to 1, the overall gain AF becomes infinite. That means to say, even there is no, practical AC input is present, still the oscillator circuit gives enormous amount of voltage gain, okay, or the magnification or the amplification factor. Now, due to this, very high closed loop gain, even the slightest noise, okay, which is present in the resistors, gets amplified into a bidirectional signal. And when that bidirectional signal is then shaped using the elements of feedback network, results in a sustained oscillator waveform. Okay, so that is the concept about oscillation. Okay, so let me tell you once again. So when A beta is equal to 1, you get a very high amplifier gain. Ideally, the amplifier gain is infinite. Okay. Now, there is no physical input signal. Inputting oscillator. That's the reason I'm writing this in prior only. Okay, that means to say the block diagram looks something like this. This is A. Okay, this is the exact block diagram for oscillator. This is A. This is beta, the feedback factor. This is V naught. This is how the voltage is tapped. Say this is positive and this is negative. All right. And I'm just giving you the leads in dotted lines. And I'm just mentioning that this is VI. Okay. This is VI. You're understanding, right? That is voltage at this point and this point is VI. Okay. But no Vs. That is Vs is equal to 0. That means to say external input Vs is equal to 0. Okay. And let us say some initial noise Vi is applied here. So this noise Vi gets amplified into V naught. And what is V naught? V naught is A into Vi. Okay. And that same A into Vi, okay, is fed as the input to the feedback network. So what voltage you are feeding here? You are feeding V naught, but V naught is equal to A into Vi. So when you feed V naught to the input part of the feedback network, the feedback network gonna give you an output signal which is called as VF. Okay. Now what is VF? Can anyone tell me the value of VF? VF is equal to beta into V naught, and we have already seen in the previous section that V naught is equal to A into Vi. So value of VF is A into beta into V naught. So in case of oscillator, in order to have a feedback signal, okay, in order to have a feedback signal which is equal to the output signal, the product A beta should be unity. And this condition is called as the magnitude condition. Magnitude condition for sustained oscillation. Okay. I've already discussed in terms of equation that when A beta is equal to 1, AF going to be very, very high. Okay. So when A beta is equal to 1, your feedback signal is equal to output signal. And the same feedback signal VF, is going to act like the input signal to the amplifier. So even when there is no physical input, that is, even when Vs is equal to 0, the oscillator circuit, still be getting the input Vi through the feedback mechanism. Okay, and this concept is called as the oscillator operation. Okay. So A beta is equal to 1 is called as the magnitude condition for sustained oscillations. And I have told you in the beginning that both Vi and V naught should be in phase. That is, total phase shift of the circuit or the total phase shift of the loop should be 0 degree or 360 degree. Okay. So these two conditions are called as the oscillator condition. So one condition talks about the magnitude and the other condition talks about the angle. So this is called as angle condition. Okay. So these two conditions are basically, proposed by a telecommunication engineer called Barkhausen. So that's the reason, this is called as Barkhausen criteria. Okay. Let me write it. This is called as Barkhausen criteria. Okay, so Barkhausen criteria, he stated two criteria, magnitude criteria or magnitude condition and angle condition. Okay, in nutshell, you can say that magnitude condition is when A beta is equal to 1, that is the product of amplifier gain and the beta factor is unity. And the angle condition is that angle of A beta, that is the angle of entire loop is 0 degree or 360 degree. Okay. If a circuit satisfies the magnitude condition as well as angle condition, the circuit gives sustained oscillation. Sustained oscillations in the sense, the output will have a constant amplitude and frequency. So that's the meaning of sustained oscillation. Okay. So that is what is called as the oscillator concept. So the oscillator concept is derived from basically the closed loop concept in which positive feedback is employed. By employing positive feedback, one can get a very high amplification. And due to this very high amplification, even a noise signal can be amplified to considerable, magnitude. And later on, with the help of feedback circuit, that waveform can be tuned into a proper sinusoidal waveform. Okay, fine. Now, what is this noise signal? I've been talking about this noise signal. So from where will I get the noise? Okay. Or how will you get, the input waveform in the first go? In the first go, in the sense, let us say I construct an oscillator circuit with the help of RC coupled amplifier, and I will couple, some capacitors and resistors to form a feedback circuit. Okay. And I'm going to connect this particular circuit to an external DC power supply voltage, right? Now, the moment when you turn on the oscillator circuit, what happens is that the circuit draws power from DC, right? Because the oscillator circuit is connected to DC power supply to drive the DC conditions in the transistor. So the moment when you turn on the oscillator circuit, there exists power transients or simply the transients. So basically, the transients will drive the oscillator operation. Okay, in the sense, the moment DC power supply is turned on, okay, this is your oscillator circuit. The noise which is present in the resistor, see, resistor is a conductor element, right? Now, in conductor element, there are excess electrons. And due to this excess electrons, what happens is that these free electrons, they move in a random path, due to which, there will be a noise signal. Okay, some noise signal. And these noise signals, normally they are bidirectional in nature because their path is highly unpredictable. They move in, crazy path. So basically, it is untraceable bidirectional path. But the amplitude of noise signal generally in the range of micros of volts. Okay, very, very low voltage signal there. Okay, so this noise signal in the first iteration itself is used as input to the oscillator circuit. What you have seen in the operation of oscillator circuit is that when beta is equal to 1, the amplifier gives infinite gain. So due to this infinite gain, or due to this very high gain, a microvolt signal, gets amplified to some volts level. Okay, so this microvolt signal is, amplified to a level which is normally there in few volts. Let's say now the wave condition is something like this. Okay, let's say this is my V naught. Let's say again it will be a noisy signal. Okay, but let's say the highest amplitude is in some volts. Okay, let's say few volts. Okay, so the first task is accomplished. That is a very low amplitude signal you have scaled up to a volts level. Okay, but this is again, a very bad sinusoidal waveform. Okay, so it is not having any practical usage. So what we do is we use beta factor. So beta factor is basically the gain of the feedback network. So in the feedback network, you will have something like fine-tuning elements such as potentiometer. Okay, potentiometers, or you can also call it as variable resistors. Or in some oscillators, in place of potentiometers, you will have, variable capacitors. Or even in some oscillator circuits, you will have variable inductors. Or in other words, what I can say is that in the feedback circuit, you will have these passive elements which are meant for, tuning the wave shape of the circuit. So by tuning either, the resistance value or the capacitance value or the inductor value, this irregular sinusoidal waveform can be shaped into a proper sinusoidal waveform. And this is what is required. So this is your end output.
आखिर अपने लिए कौन बनाता है तो अपनों के लिए होता है डाउनलोड पावर
I think that was his alarm to get up for the afternoon class. Okay, I have muted him. All right, so this is the end output. Okay, this is how the oscillator process takes place. Okay, simple topic. I think I only have little extended because it requires a good understanding. Okay, to understand oscillator circuit. Okay. All right then. So what I will do, I'll stop the class at this point. In the next class, let me talk about the aspects of oscillator circuits. All right.